Hey, Sean, are you there?
Yeah, yeah.
All right. Well, how's your morning going for you?
Pretty good.
Good, good. Well, did you guys get snowed in?
Yeah. We had a
That's,
lot of ice as well. We had like negative 20, 25 wind chill.
oh my goodness. I definitely remember those days. Uh, yeah. I remember, I always remember -50, and that was way too cold. -12 I can handle, not -50. I said, I'm done. Well, how about classes? Did you guys go online or it's just missed class for a few days?
We just missed class for a few days.
Okay. Well, I guess you didn't have your exam then.
Yeah.
Well,
It
how you
ended up
feel?
being a good thing though, because my teacher decided to curve our tests.
Oh, nice.
That way we didn't have to like do corrections afterwards.
Oh, okay. Okay. What'd you get on it then?
I mean, I haven't done the test yet, but like it's on Tuesday.
Is what?
It's on Tuesday.
Oh, okay. So there wasn't a last test occur, but it's going to be the next test.
Yeah.
Oh, wow. That's interesting. They decide the curve before they give it to you. Uh, well, how you feeling about it?
Um, Pretty good. I said pretty decent.
Okay. Now, which topics are going to be on it?
Um, Optimization for one, and then mean value theorem,
Okay.
like first derivative and second derivative tests, and like cavity.
Okay. Curve sketching, is that also going to be on it?
Yeah.
Okay. Okay. Um, Now, did they give you some practice problems to work on so you're ready prepared for it? Or
Yeah.
okay, let's take a look at them. Why don't you throw them over here on the bit paper and let's see what you have and pull some problems up too if you need to.
Yeah. Before I do that, could we work on this like problem number 10?
Yeah, sure thing. Okay, so let's see. Power station. Oh, the last one we left on last time. Hmm.
Yeah.
Okay, so how far did you get on this one?
Not very far. I was like confused on what the question really meant.
Okay. All right, give me one moment here. Let me get some stuff. Give me a second. Okay. Okay, so a power station on one side of the river is going to be half a mile wide, and the factory is 6 miles downstream on the other side. It costs $60,000 per mile. Wow. To run power lines over land, and 85,000, my goodness, per mile to run them underwater. Find really the most economical path for the transmission lines from the power factory to, or the power station to the factory. Now, what did you do? Okay, here's our diagram we left off on. Now, the thing is, we're not quite for sure. Let me just pull it down here so it's a fresh, new perspective. We're not quite for sure how much we're going to go over land and how much we're going over the water, right?
Yeah.
So when we can sketch out our diagram, when it goes so far, we just don't know how far, and then we're going to make a beeline. Now, let's say from here to here, we have a distance of x. And if it's 6 miles altogether, what's this distance here?
Um, X 6 minus X.
Okay, so if this is 6, and then altogether you would have something like here's 6 minus x. Now, this right here would be something like maybe if you're going across the land, then you're going to be going across the water from there. Now, look at the cost function. The cost of land, distance of land, underwater cost, distance in water. If I go across the land, how much is that going to cost us?
Um, 60K per mile.
Okay, so we'll have our 60,000. And the miles that we're going to be doing, something like 6 minus x. Then the underwater, 85,000, and that's going to be multiplied by x. Oops, not x. Let's back up. Because the actual distance is here, isn't it?
Yeah.
Now, look at the other one. The power station is on one side of the river is a half a mile. So if I was to drop down B line, half a mile. Could you figure out what that distance is now?
Um, Not yet.
Pythagorean theorem.
I mean, yeah, but like, oh yeah.
Okay, so we'll have x squared, and then we'll have a fourth. So here we'll have our square root x squared and our fourth. Okay, there's our cost function. And what do we need to optimize?
Um, we need to minimize this function,
And if I want to minimize it, I got to find
the derivative.
the derivative. So let's go and do that real fast. Not 6. The derivative of 6 minus x is,
Oh yeah, yeah. I was just kind of extending it out.
oh, I see. Now, I wouldn't expand it. I would just leave it the way that it is and take the derivative on the inside because the constant's not going to matter. Perfect. And on the inside, you got it. Okay, so there is your derivative. You would then set your derivative equal to 0. Oops, actually the derivative for x right there, that's going to be 1, so that shouldn't be there. But the set your derivative equal to 0 and find the critical values now. So I have the square root x squared plus a quarter. Okay, how would you take this and solve for x? What's your next step?
I would move the 6,000 to the other side.
Perfect. Let's keep going with it. Okay. And I would divide out some zeros here. Makes it a little bit easier. And unlock the x. The x is trapped inside the radical. So in order to unlock it, we can
Um,
square both sides. Let me give you more space here. So square the left, square the right. Now you have x squared and a quarter. And you have 85 over 60. We can reach it down further if you like, but there it is. Okay. Now, does that make sense? Yep. And that's going to be your critical value. Now, also know there are some restrictions placed upon x. What's the lower bound x could be?
um, uh,
It's not stated in the problem, but it's implied within the problem. So you got to read between the lines. Literally, read between those lines. X refers to the distance. Could the distance be negative?
no,
Could it be zero?
no.
It could be. You could just decide go all the way across and then go straight down. So it could be zero. What's the maximum value it can be?
Um, half.
Not half.
No,
What's another option you could do?
um,
You can go straight down. We can decide go so far, then go down, or we can just decide to not go across the land at all and just go across the water.
there'd be
A maximum of six. Good. Okay, so what we have here is if we take our x value and if we were to simplify it, we should come up with this. And we have our lower bound and we have our upper bound. So what I have here is I got a problem. It's on a closed interval. And when it's on a closed interval, we're talking about absolute extrema. We can talk about absolute max, absolute min. The next thing you would do is you do an evaluation at each one of these values just to decide which one is it. So you go back to your cost function. Let's pull that down here.
wait, real quick.
Mhm.
Wouldn't it be like the square root of 6 squared plus 1/4? Because that'd be like the minimum distance it'd take to go over water.
Yeah, that's what it's going to be in the end. It's going to correspond to this piece.
Ah,
But in general, this is how you would work through these problems. You have to check the bounds and you say, okay, it doesn't make sense for this one. It doesn't make sense for this one. Also, when you go from a quantitative perspective, look at the number behind it. You say, okay, that's too big. It's small, but it's not small enough. And you say, okay, this right here, that's going to be the best option.
wouldn't this be like the upper bound?
Mhm. That's exactly what that would be.
So then why do we have like the 6 here?
Six is going to be um, the biggest that you're actually going to get, the cost
Oh,
of it.
for X. Oh, okay,
That's
okay.
right.
Not for like the total distance that we travel.
No, let me see if I can get these in a moment. Okay, so if you actually crunch the numbers out, this is what you're going to get. Okay, you can see, okay, zero is kind of small, six is a little big, and smack dab in the middle is our critical value that we looked at. Now, reason tells us, yeah, that's going to be the case. We probably didn't have to really crank this out all the way. But what if you had an additional value up here, Sean? What if you found out in a problem, maybe they just had another critical value? It's going to be a little hard to decipher them, which one's which. So take it and plug it into your function in the very end to see what's going to happen. So here are the steps when you're looking at your optimization, your extrema values. The first thing is you do want to get your function, whatever it's going to correspond to. If they give it to you, great. If not, you're going to have to develop yourself. But you do want to find your critical values because that is going to be very critical in what lies ahead. And then once you have your critical values, you want to check endpoints also. Now, this is what's going to happen when you're on a closed region. So if you're from A to B. Critical values, this is what corresponds to what's known as your relative extrema. And we put in the end values, the endpoints, then you have what's called your absolute extrema. And then you can talk about optimization. Good. Now, does that make a little bit more sense to you?
Yeah.
Okay, well, let me throw you this problem. It's a little bit different here, but see if you can put this together. Okay, so tell me what's going through your mind as you're working through the problem.
Um,
What are you seeing first?
I'm gonna have like a circle on both ends
Okay,
and
so
try and find the surface area.
right, so you're constructing your diagram. That's perfect. Now, the way that I do that, yeah, just like this. And I also see that we have a cylindrical soda can. So when you see that, that's a buzzword. What do you think about?
Pi r square.
Okay, we do think of pi r square because we're talking about maybe the area of a circle. What else do you think about?
Um,
It's something you drink, like or something from a cup.
like a soda can.
Yeah, I think of volume, right?
Yeah.
What's the volume?
512 cubic inches.
Well, how would you calculate the volume in general?
Um,
Okay, tell me where you have a two there.
because I'm using X as my diameter instead of V.
Oh, I see. That would be fine then. Now, if that's going to be your diameter, we're going to have to change it up a little bit. It's not really a two because if you have volume, you're going to be pretty much stacking up a bunch of circles, a bunch of disks on top of one another up to a certain height. Pi r squared times your height. And if you're using x over 2 as your radius,
Oh, oh, yeah.
it's going to be 4. Okay. Now, Just a quick question. Why did you decide to do diameter as opposed to doing radius?
Um, I didn't want to like forget later that I did radius instead of diameter.
Okay. It's fine to use diameter. There's really nothing wrong with it mathematically speaking. A lot of problems though, the R calibrated the formulas. You can't do it in terms of diameter, but a lot of things are in terms of radius. Like what's the area of a circle? It's pi, not diameter, but it's radius. And when you look at the formulas, oftentimes for volume of a sphere, it's also not in terms of diameter, but it's in terms of radius. So radius might be a better option when you look at the formulas, so you're not going to misalign them. But you could do diameter. You just always have to make sure you have to calibrate it for diameter.
Hmm.
Okay. Anyways, let's keep pushing on.
Oh,
Okay. Now tell me what you're doing here.
I was trying to find what y is equal to, and
Okay.
then
So why are you trying to locate y? What's your idea?
so when I'm doing surface area equation, I can use x.
Okay. I see where you're going with this. Okay, so that's 2 pi x. And are you using x to be a diameter still or the radius?
The radius,
Okay.
and then
Now be careful of that last piece.
oh,
That's right. So you have two circles on top. And this piece right there, can you elaborate on that?
so this is like I think this is the equation for circumference
Okay. Let's don't think.
times
Let's be certain. So here's what you can do. Deconstruct your can. If you take it and if you unravel it, you have two circles on top and you got this thing in the middle. What's that thing in the middle?
um
It's going to be a rectangle when you unravel it, and then you're going to roll it back up. Here you would have a height, and this piece right here, as you roll it up, it becomes that right there. It's like, can you see this piece of paper?
yeah, wait,
It
yeah,
Okay, so if you take the piece of paper and if you were to roll it up, do you see what's happening?
yeah,
That length is called on a circle, circumference. So that's why this is going to be your 2 pi r. And since you're looking at area, it's 2 pi r h.
yeah. I just read like the equation for like just the straight up circumference of a circle.
Good. All right. So there's our surface area. See if you can take it from there. Okay, so after you take your derivative, you would. Now, there's a slight mistake here. Let me help you out. Check your coefficient there real fast. You see that the mistake? There's a 2 pi to begin with. And take the derivative, it'd be 2 times 2. So if you
Yeah, but I
choose.
divided both sides by the two.
Oh, okay. When you okay. Um, when you got over here, you're saying. Okay, that's fine if you do it over here. Just if you do it over here, mathematically speaking, it's not technically correct, but you can
Yeah.
go ahead and factor it out, then divide it out like you're doing over here. I see now. Okay, yeah, go and keep going. Yep, you got it. Okay, how you feel about the problem there?
Pretty good.
Good. Okay.
And then I can solve for my life with the
Mhm. All right, so what I'm gonna do is I'm gonna throw you one more. It's kind of a can also be a challenging problem. Let me give you a moment here to think about a game plan, how you're gonna tackle this problem.
pretty sure I did this like exact problem yesterday, except it was 30 feet instead of 8 plus
Oh,
5.
really?
Yeah.
Well, if you understand it, that's awesome. You can
Are
see
we
these come up quite a
including
bit.
are we including like this side for the rectangle as part of the perimeter?
Perimeter would just be this piece here and all the way around.
Okay. So then I don't know why I started doing area there.
That might be useful. Because you have two variables, you do need two equations, and area does give you an extra equation.
Be x plus 2y plus um I x squared over 8. And then hmm, looking confusing.
Okay, so what part's confusing you here? Is it the way it's being set up?
I mean, I don't know how I'm gonna like substitute this in very um easily.
Yeah.
Oh, I did the wrong equation. I did that for area as well. That would have made it much simpler.
Okay, just pull a note up here. That's for the rectangle. That's for the circle. And next again, it's going to correspond to your diameter. Okay, so this right here, this is very convoluted. Do you see that?
Yeah,
And you're solving for y. Here you would have 8 plus pi. And here I do have x's here. I could combine those x's. You see how I can combine them? Just factor it out, just like this.
yeah.
Okay, then I would take this and just throw it to the other side and then divide by 2. Now I can combine it further, and that'll get me 2 plus pi up top. And when I divide everything by 2, since there's already 2 there, you get 4. That's what I would use for y. Then I would take it, I would drop it, and then I'll just keep cranking this out. Now, the the problem here is you have to put two geometric shapes together. It's easy to understand, but it's a little hard to really get it going because there's a pi in it and it's things you're not really accustomed to because usually you would take like 2 plus 1, you compress it down to a single number. Now, what I want to do is I want to share this with you over here. Can you see the screen okay?
Yeah.
Let me see if I can get that in. I'm having a hard time. Okay, there we go. If you come over here and over on the website, look on the differentiation section, click on the applications. Here's some stuff on optimization, some nice little notes to help you remember what you need to do here, Sean. Find your relative extrema, absolute extrema. But come down here to the problem sets, click on the optimization. Here are two problems you can review later on. And here's the number window problem. And let's just walk you through it with this example. And it's just going to show you how to go about this from a abstract perspective. I'm not going to be plugging in 16 feet, the piece has provided. I'm just going to work it as if it's not there. And then I'm going to plug in at the very end. Now, doing that can sometimes help you find mistakes before they emerge because whenever you start plugging in the numbers, the things go away. It's hard to find those mistakes. So go ahead and look at this one later on, this video, and the other one up here is just another example on the optimization.
Okay.
Okay, and let me just kind of go through that real fast. There's a nice little formula that we come up with in the very, very end. Okay, now, does all that kind of make sense with the normal window?
Yes.
Okay. Now, was there a question that you really want to look at here today?
Um, Not really. Every question I've been able to like get my way through it.
Okay, that's pretty good. Okay, give me a moment then. Let me see if I can locate something else for us. Okay, here's a problem from an old AP exam. Actually goes back to 89. And here's some things on curve sketching. Okay, now here's the first thing that you ever want to do when you're looking at your graphs, Eshan. This is important. You have to recognize, is it graph of F or is it graph of F prime? Because it's real easy to get tripped up on that. So you always want to take a moment and just see what they really were referring to. So this is the graph of the derivative. Okay, so we're looking from a closed region from negative 10 to 10. For what values of x does the graph have a horizontal tangent line? Now, if you don't recognize that's f prime, you would say it's going to be here, here, and there. But that's wrong. To find a horizontal tangent line, you need your derivative to be 0. It's going to be here, here, and there. because those are going to be the x-intercepts. Okay, what about when the graph has a relative max? How do you know when a graph has a max or has a max or a min?
Um, it's a min if it's going from like positive to no, it's a min if it's a max if it's going from positive to negative, and it's like a min if it's going from negative to positive.
That's right. So here's going to be your minimum value, and your maximum values. How about concave downward?
Um, that's when it is increasing or decreasing. That's when f prime of x is increasing or decreasing.
Okay, so if you want to find f prime corresponds to the monicity of the graph, where it's increasing or decreasing. When you look at the change in the monicity and analyze how fast that's changing, that's when you have concavity. So you look at the second derivative. So when you look at the second derivative in terms of concavity, you are looking at the derivative's derivative. So you are looking at a critical value of the derivative. That's going to be up here at those locations. So if you can remember the second derivative is the derivative's derivative, it makes it a little bit easier. Okay, let me throw you this one now and see if you can actually sketch this graph. Oh, that works just as good. There you go.
So as that's a min, this one's a max. Decreasing in this interval, increasing in this one. Oh, oops. Um, I'll have to.
Yeah, I think you're okay with that.
But then it'd have like another. Oh wait, no, there is another max at F0.
Yeah, just gotta put that nice bend in it.
And then I'll just go
Go
down
down.
forever. I didn't realize that there's a max at F0.
No, you did a pretty good job there. Okay, let me see if I can see if we can upper game a little bit here. Okay, all right. Here's a little bit of a different spin on it. Here's another AP exam question. Comes back from 93. You want f to be a function, and notice here, see that? It's constant. Okay, so that's going to come up in question C. We're going to have to kind of analyze what's happening with the graph. Okay, good.
Just want to drag all the way down. Put that off to the side. Basically, for what intervals is this positive? So
Okay. Okay, there's your number line.
this one's going to be positive, which means it's going to be a min. And this one is going to be a max.
Good.
And then I got to do the same thing for f prime of f, same derivative.
These are 5/3 over here. Negative on the left. That means concave when it's negative, concave down, then concave up.
And then so that means that 11 equals x cubed minus 5x squared plus 3x plus k. And we know it's a relative minimum, and we know the only relative minimum is x equals 3. So
You showing you're rocking it out.
that'd be k equals 20.
What questions do you have about this problem?
I don't think I have any.
I think you did good, pretty well on it. Okay. Here's another AP calculus question. Okay. Have you seen questions like this yet?
Not like this.
Okay. Notice how it is curve sketching. It's in terms of a table. In the first row up here is talking about the function evaluation. And then you have your first derivative and your second derivative. So it's going to be real similar to what we did up here. We had these intervals where it's going to be positive or negative. It's just they're making it a little bit easier to see in terms of a table. Okay, so see if you can figure out a nice rough sketch, get some kind of inferences from this, and then does it have a relative max or does it have a relative min? Okay, so you use the same skill set on the last problems on this one. Okay, I'll give you a moment to read it over.
So at 2 it has a min, and this is a point of inflection, and another one right here.
Just remember the emojis for the concavity. Oops, there we go. So make that a little smaller.
And then point there. And then 3 is 0.
Okay.
And then there's going to be a cusp at 2. And it
Okay.
also changes concavity at 2
Why is there a cusp there, you think?
because it's a point that doesn't exist on f prime of x. and it's not differentiable on a cusp.
Right. So you can also not exist because maybe there's a jump in it, but it is can be differentiable except for it too.
It's also going to change in cavity, so
Mhm. And
probably
that's what
not.
a cusp is.
Oh shoot. Alright. How would I like draw this out?
Like a cusp, just kind of go up and then go down.
It also like changes concavity, so in this like case, I don't know, like
Okay. So concavities, they can change because you have an inflection point like this. That's a possibility. Or it could change because of that. That's another possibility. Yeah, it's a little hard to see, but yeah, I can kind of see it went like that.
it keeps going downwards over there,
Yeah. Okay.
so it doesn't do anything at four. Keep going down like this. Actually, we wouldn't know because we don't know where the zero is, so it could be either way, I think. Yeah, that cusp can like confuse me a little.
Okay. Okay. Does it make a little more sense to you now?
Yeah.
Good, good. So if you see this on your exam, you're going to do well in it. Okay. So let me just throw you some general guidelines when we're sketching the graph. So if they ask you to sketch the graph, these are the things you want to find. And I'm going to throw you some problems here to think about later on today. And let me throw you a few more. These questions right here I'm about to give you, these are questions, real common questions that you're going to maybe potentially see on an exam because it has a lot of concepts in these kind of questions. So what I want you to do is uh, practice a few of these problems up here, Eshan. Pick a few of the polynomial ones and pick, let's say, two here, pick two here. See if you can graph them out. I think you're going to be okay with it. So you don't want to spend too much time on it. I think you're going to struggle a little bit more when you get to the concept questions. So you definitely want to spend some time thinking about this question and also
Okay.
thinking about this question down here. And let me see if I have another one for you. Okay, so think about these, work these out, and if you get stuck on it, send me a quick text, an email, or something, and just let me know.
Okay, yeah, sure.
All right. Well, Eshan, um, you feeling pretty good with everything else then?
Yeah.
Okay. Well, keep up the good work. If you need anything, let me know. Other than that, I'll see you next week and good luck on your exam.
Yeah, thank you.
All right, you take care.
You too.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.